So here today we are talking about enhancing the spatial resolution of satellite-derived land surface temperature data. Basically, the idea is we have ecostress, which is at 70-meter resolution, and it offers a great temporal resolution of observations, but the spatial resolution is 70 meters. And a few years ago, I would have said 70 meters is more than enough. I mean, who are we kidding? 70 meters at a city scale is so much more than we need to see at this point. But then when you talk about intervention, and where exactly do you need to solve some problems, then a 70-meter scale is not enough to see the roads or the parking lots, or you can see large parking lots, but the roads are most often lost in that resolution. So we are trying to downscale it and make it better. The other product that we use in conjunction with EcoStress is Landsat 8. The resolution of Landsat 8 is 30 meters. So, sorry. So it's in essence, what we are doing is downscaling, but it can also be called sharpening because we are providing a sharper, higher quality image. And every pixel that you see in any corner of the EcoStress image, we're going to break it down into its constituent, whatever makes up that block appear a certain temperature. You have to always remember that whatever temperature we see from the satellite is never the real temperature of that block, because in that block you have all sorts of surfaces from the rooftop to the ground, and you have some little sidewalk trees and grass, and the walls of the building also contribute. So the representative temperature of any pixel is not the real temperature of that land block, but it is an aggregate and an average of all the other surfaces that contribute to that temperature being as such. The factors that contribute to that temperature are, like I said, all those surface properties. But if we break it down into some metrics, that will be one, the reflectance of the surface and the absorbance of the surface. How much heat does it absorb and raise its own temperature, and how much heat does it reflect, that we can measure from satellite, that is the reflectivity. So there are some properties of the surface that we know that help us predict the temperature that will be. So that is called albedo. Albedo is essentially, if you think about it, it's the aggregate reflectance of all the frequencies. So that's called albedo, but you can just think of it as higher reflectance. It varies from 0 to 1, where a 0 albedo will be just absorbs everything and doesn't reflect much back, and 1 will be like a mirror shining it all the way back. Then we have the NDVI, which is normalized difference, normalized difference in vegetation index. It is just a measure of vegetation. So it also varies from 0 to 1, where 0 will mean there is no vegetation there and it's all dry. Either it could be grass, but it could be so dry that it just shows up as no vegetation, or 1 where it's just green and lush with crops or forest or any other kind of greenery that we know. It can also have negative values over water that you'll see in the plots later. So what we know is these things do correlate with temperature. And the idea was, if we can derive the LST predictors like NDVI, albedo, and any other metric that we know of, and if we can predict what the LST might be, because those other predictors we have at 30-meter resolution from Landsat. So what we start with is we have two images that we get. One is fine scale, that is from Landsat, and one is coarse scale that we get from EcoStress. EcoStress provides LST directly as a product, and from Landsat we download what is called surface reflectance and calculate these properties like albedo and vegetation index. So first we have to make sure that both are, to actually compute anything on the two rasters, we have to make sure that they have the same resolution. So we start by making it go either way. Either we upscale the 30-meter resolution to 70 meters, or we can downscale 70 meters to 30 meters. And you'll see that we do both in the sharpening tool. If you don't follow this workflow, don't worry at all. I'll be honest, I didn't understand what this is until I ran the code. So once you run the code, it's so super simple that you'll understand this. Anyway, so wait, I'll just let this. Yeah. So the idea is, once you have these two images, you use albedo and NDVI to predict LST using the model. The model basically is, it could be one of two things. It's one is the HUTS. It's the Urban Thermal Sharpening Tool, which is essentially a regression model. So it's an equation that uses two inputs, albedo and NDVI, and gives an output of LST. But it also uses the LST that we get from ecostress and combines the two to get a downscaled, lower resolution, higher resolution land surface temperature. But this model part is what's variable. So the workflow is typically the same in whatever, anytime we do any kind of downscaling, but the model, what exactly is the relationship between these predictors like albedo and NDVI, and how do we get to LST from only those, is what varies. So what we are using in this tutorial is HUTS, the high resolution urban thermal sharpening model, but we are also working currently on a random forest model that might be able to do the same job or better job. So we are working on that part. Don't worry about this one. It'll come up in R and it'll be much clearer when we talk about this in R. Now, visually, like Katie said, that it makes more sense to see these things visually and that'll drive more action. And for me as a student, I also think that we understand better when we see visually what exactly is happening. So here is an example of the images we were talking about. EcoStress LST, that is a product at 70 meters. And here are the other two products that we get, the NDVI from Landsat 8 at 30 meters and albedo from Landsat 8. Now, if you notice, the albedo goes from 0.1 to 0.8. Albedo always varies between 0 to 1. And lower albedo here, for example, is the absorbing part, the mountains, the greenery, and here are the lighter concrete pavement path that just reflects it back. Here is NDVI, in which we see that vegetation is higher up here in the mountains and the forest, and the urban areas have a very low NDVI, especially the road networks and the parking blocks and the building rooftops. They almost tend to have a zero NDVI, no vegetation there. So these are the rarer parts. A better example of what we talked about. So the relationship between NDVI and albedo is not necessarily linear. You cannot say that if the albedo is low, the NDVI has to be low. So there are 4 quadrants in this, for example. One is if you have a high NDVI but low albedo, that's just green vegetation. It's not reflecting as much because the green areas, they absorb a lot of heat that's given on them, but the vegetation index is super high. So those areas will be cool. The color here indicates temperature. So there are 2 ways to be cool here. One is if you just have vegetation and they're giving off, they're absorbing as much heat as possible. So that's here. And then you have the other corner where you have no NDVI, that is dry, non-vegetative surfaces or dry grass. So it can be vegetation, but it's just dried out, which gets hot. And the albedo is also really low. Or the other side here is reflective roof. So that's the urban intervention that we do, because we cannot have, beyond a point, we cannot have NDVI to be too high where the residential or the commercial buildings are. So so we can do reflective roofing though, and that'll cool it down by increasing the albedo. And that's another way of cooling down, even if we can't work on vegetation. So this side is the green roof kind of intervention where we just apply green roof or green walls to cool down the buildings. Or here is white roofing or reflective roofing solutions. So this is a very handy plot that will just help us remember that NDVI and albedo together help you predict what the temperature might be. So the algorithm that we're going to use uses these 2 inputs, and we try to predict what the LST might be. And here is the equation. So it's a multivariate regression model. And we have the code, we have the coefficients that we found out by fitting it, and we have provided it in the R and MATLAB code. So this is the model that we'll be using. And in the end, there is a factor that you see, the DLST energy balance conservation. So that's the LST of the day that we'll use from EcoStress. And so this is the model where we use NDVI and albedo. Alpha here is the albedo. And then we have the LST from EcoStress that we'll add. And the results should hopefully look like this. Now, there are a couple of problems that we might run into if there's cloud cover or if the image is not exactly overlaying on each other. But if we get lucky and we find the right images to work with, then eventually the solution should look like this. Basically, you see the low resolution EcoStress model here at 70 meter resolution. And once we apply the sharpening tool, it'll be 30-meter resolution, where more and more roads are more clearly visible. So here you see this area, sorry, this area becomes sharper, uh, and more information can be gained. Now, from a solution perspective, this image is much more helpful in driving change, because we'll know exactly where the hotspots are emerging and what exactly can we do with it for each and every city. And in here, you can see that we can now distinguish a lot of features that were not visible earlier. For example, you can see the runway and the airport here, and you can see downtown Los Angeles, which was earlier just a mess earlier. So this is why it's clearer to see it. And in fact, on if I mean, you have to work really hard to find them, but once you find them, you can see the white roofing and the black roofing also, whatever is going on, and you see that the temperature indeed is cooler for the white roof reflective surfaces, and the black surfaces just absorb and get hotter.